My grandma used to make the best Belgian mussels with a creamy white wine sauce. I kid you not, I still use the recipe to the delight of our house guests. And every time I complimented her on the deliciousness of this delicate dish, she would say the same thing. Flattery will get you everywhere. So let me start by saying that I am honored to speak in a room full of some of the most important people in the world, or at least in Europe. I'm serious even. I've lived in various parts of the world, including China, Southeast Asia, and the Middle East, and the only place where I would trust eating grandma's mussels without question is right here in Europe. Maybe I shouldn't, you tell me, because I know, now even more than before, that there are people standing watch over our food safety risks. You are the guardians of Europe's food safety. You're the ones who assess these risks, who create the recommendations, and influence the standards that protect hundreds of millions of people every single day. You are why people can feed their kids a wide range of nutrients without a daily worry of how it may impact their development, and for that I salute you. I've seen what it's like when this is not the case. Now, to kick off this story, I think it's reasonable to divide this into a few chapters, starting with how did we get here? The ambition of transforming our relationship with knowledge and information isn't a new endeavor. It's ancient. We've always wanted to collect, organize, and preserve intelligence, almost as if we were preparing to build machines that think even before we had the technology. One of the earliest known machines for capturing knowledge was the Antikythera mechanism. Built by ancient Greek engineers over 2,000 years ago, this complex gear-driven device could track planetary positions, predict eclipses, and model celestial events with incredible precision. It was essentially a mechanical model of human knowledge about the solar system. Then there's the Library of Alexandria, one of the ancient world's most ambitious projects. Its goal was to collect all known knowledge, an early attempt to organize and preserve intelligence and make it accessible on a massive scale. Imagine the influence this knowledge hub had in its day, serving as a center for learning and discovery. It was also a scientific hub where academic research flourished. Consider the Rosetta Stone. Discovered in 1799, it provided a key to understanding ancient Egyptian hieroglyphics, allowing us to unlock knowledge that had been hidden for centuries. It's a reminder of the human desire not just to capture knowledge, but to make it accessible and understandable across boundaries, a challenge we still face to this day, and where AI is already playing a major role. Then came Gutenberg's printing press in the 15th century, a true game changer. Suddenly, knowledge wasn't restricted to a privileged few. Ideas, philosophy, science, they could be distributed and shared. This wasn't just preservation. It was the beginning of knowledge expansion and democratization. In the 19th century, Charles Babbage designed machines that could process complex calculations, the first step toward programmable computing. His difference engine, an early mechanical computer, laid the groundwork for capturing not only knowledge but also computational processes. His vision was to create machines that could handle some of the tedious manual labor done by humans who would be prone to making mistakes. You can see it at the London Science Museum. This monstrosity weighs 5 tons and contains 8,000 parts. So from ancient mechanisms to vast libraries and early computational engines, humans have always been driven to capture and extend intelligence. Each of these steps represents another milestone in our desire to externalize human thought and ingenuity. By the 20th century, technology had advanced to a point where these ideas could evolve into something new. Enter Alan Turing, a visionary who asked a pivotal question: can machines think? With that question, Turing set the stage for the modern field of artificial intelligence. Turing's idea of testing machine intelligence through interaction became the foundation for defining intelligence in machines. It wasn't enough to just capture knowledge anymore. The new goal was to create systems that could use that
Hello,
knowledge
dear
in
EFSA
ways
managers.
that
I'm
mimicked
Alan.
human reasoning.
Or rather, I used to be. I once asked, can machines think? But perhaps the deeper question is, why do we humans find this so endlessly fascinating? The pursuit of intelligence, in whatever form, may be humanity's most intriguing ambition. You see, the Turing test wasn't meant to prove a machine's humanity. No, it was a thought experiment, a way to stretch our understanding of what intelligence might mean in a world where logic and emotion overlap. Machines might not think as we do, but could they think enough to fool us?
Building on Turing's vision, AI researchers used rigid, rule-based systems. These programs, like the logic theorist, could solve mathematical problems from the Principia Mathematica, not Newton's one, Bertrand Russell's one, but only within narrow, predefined boundaries. It was a first step, but a limited one. Rule-based AI proved too limited for more complex real-world applications. These systems could follow commands, but couldn't adapt or learn independently. By the 1980s, AI researchers were starting to move away from strict rules. Instead, they trained systems on data, allowing machines to recognize patterns, opening up new possibilities for AI beyond rigid programming. An early use of machine learning was fraud detection, where data patterns helped flag suspicious behavior. Rather than using static rules, these systems could adapt to changing patterns in real time. In the 2000s, the emergence of neural networks sparked a new era. These networks, inspired by human neurons, allowed AI to process information more dynamically, recognizing images, sounds, and even language. How do they work? Imagine you're teaching a young child to recognize a dinosaur without ever having seen one. First, they'd see many examples of dinosaurs, and over time, they'd pick up on certain features, like scales, bulky body shapes, and sharp teeth. Neural networks work in a similar way. They're trained on huge amounts of data, and as they go through more and more examples, they get better at identifying patterns. The key difference is that, unlike early rule-based systems that followed strict instructions, neural networks learn from examples and improve over time. This allows them to tackle complex tasks, like recognizing faces, understanding speech, or even playing games. These networks are now behind many of the most advanced AI systems we see today, from language models to image recognition. Neural networks are at the root of a major societal shift, even if most of us know very little about them. A major turning point came in 2016 when DeepMind's AlphaGo defeated one of the world's best Go players. Go was seen as uniquely human, requiring intuition. AlphaGo learned to master the ancient Chinese game of Go, a profoundly complex board game of strategy, creativity, and ingenuity. I remember my walks around Shanghai when I lived there, watching old people in the parks huddled around a table to watch two people face off in a game of Go. I even tried to play a few times, but I quickly realized I brought the wrong mindset to the table. I was thinking like a chess player, in logical anticipatory steps. But Go doesn't work that way. It requires a reliance on something like intuition, creativity. AlphaGo defeated a human Go world champion a decade before experts thought possible, inspired players around the world to discover new approaches, and arguably became the strongest Go player in history. It proved that AI systems can learn how to solve the most challenging problems in highly complex domains. It also profoundly challenged our previously held assumption, which is still widely held today, that computers cannot display creativity. Move 37 in the second game between AlphaGo and Lee Sedol was a game changer. It was so unexpected that it left even the top players and commentators stunned. AlphaGo placed a stone in an unusual spot, breaking with traditional Go strategies. This wasn't just following patterns. It was almost like the AI showed a kind of creativity we hadn't expected from a machine. That move was a wake-up call. It showed us that AI wasn't limited to predictable tasks. It could surprise us, even in something as complex and intuitive as Go. Move 37 became a symbol of a new era, where AI challenges and expands our ideas about strategy and ingenuity. While deep learning brought us impressive results, it also introduced a trade-off. These models became so complex that even experts couldn't always explain their decisions, leading to what we call the black box problem.
The black box problem means that even though AI can make powerful decisions, we often can't see or explain how it reaches those decisions. Imagine getting a result without knowing the reasoning behind it. It's hard to fully trust it. This is especially concerning in areas like healthcare and safety, where knowing how matters just as much as the answer itself. If we can't understand how AI thinks, we can't fully trust it or hold it accountable, which is why transparency in AI is such an important challenge.
Today, AI is everywhere, from voice assistance and image recognition to personalized recommendations. It's now a part of daily life, although the underlying processes remain hidden to most users. Every time you open an application on your phone, get a recommendation, play with Google, or even just when taking pictures on your smartphone, AI permeates the experience. But with AI embedded in so many facets of life, new questions arise about privacy, ethical use, and bias. These concerns are especially important in areas that touch on public safety, privacy, and fairness. AI is now incredibly powerful, with applications that offer real-world benefits but also potential risks. The question is no longer, can we build intelligent machines? That has now been settled, and the Turing test has been passed and shown to be somewhat lacking as a measurement of machine intelligence. The question now is, how do we build them responsibly? So we've arrived at the here and now, and I suppose the best way to look at the here and now is through the lens of what is possible with AI and what is already being done, and what any one of us could conceivably do with AI. For example, I could show you how you could very quickly generate the sorts of images I've been sprinkling into my presentation just by typing a simple prompts into one of the many image generation AI systems that have proliferated in recent years. A skill I believe everyone should master because it's a precursor for how many of us will interact with intelligent systems in the years ahead. Just a few examples of tools that make it super easy to create all sorts of creative images just seconds on any subject imaginable. Useful for presentations and science communication, which is after all one of EFSA's functions. But that's on the citizen-facing side where most of you perhaps aren't really operating, and therefore might not immediately see much use for this sort of capability. I'll leave that for you to decide. This field keeps evolving, and we're now seeing generative AI play a bigger role in how we visualize data quickly. Picture being able to feed an AI system your complex data set or reports and getting back, in mere seconds, a sophisticated visual map of all your taxonomies and ontologies. This could make it so much easier to communicate and understand these complex relationships, while being a huge improvement over our current visualization methods, which, let's face it, tend to be time-consuming and clunky. Getting this task done faster and with better quality means we can spot important patterns sooner and act on them more quickly. And that goes both ways. Systems that can generate sophisticated visual information can also be made to understand it. For example, the newest version of Claude, one of ChatGPT's most robust competitors, now has the capability of understanding the combination of visuals and text combined in one format, so you can feed it a detailed report with text, images, and graphs, and it will be able to understand that combination and help you digest and process it very quickly. Like the example given, you can give it the Apollo 17 flight plan and then have a discussion with it about the plan. Amazing. AI excels at processing huge amounts of scientific data, finding patterns and connections in minutes that might take us months to spot. Let me give you a real example. This year, Wageningen Food Safety Research used AI to scan scientific literature for chemical hazards in food. Their results? 93% accuracy in identifying known contaminants that we already monitor in our food safety programs. It's a perfect example of how AI can transform the way we extract insights from vast amounts of research. In fact, EFSA will be releasing an automated critical appraisal tool. In May of next year, I'm told that is not dissimilar in function. Evidence appraisal is, at least from what I've learned about it in many conversations, I've had a rather tedious and time-consuming endeavor. Across scientific research the world over, keeping up with the pace of information creation and making sense of that information, turning it into evidence, is becoming too big of a task for any human. So having access to an AI tool that can turbocharge this critical process while keeping humans in the loop should be a boon for all modern researchers. This isn't about replacement, but about significant augmentation. Now, even if you're not collecting data directly, it's crucial to understand how AI is reshaping assessments. Let me share a real-world example that's happening right now. The FDA has rolled out an AI system at over 300 ports to screen imported seafood. Here's what it does. It scans thousands of shipments every day, looking at inspection records and supply chain data to instantly flag anything risky. And it's working. They've seen a 10% jump in how many products they can evaluate, and they're catching 9% more violations. This matters because over 90% of US seafood is imported. This isn't future tech, it's already making food safety more effective today. Let's look at something practical from your daily work. Every day, EFSA receives questions through your CRM system, and many of these are questions you've answered before. Imagine having AI scan your Q&A database to draft initial responses, which your experts would then review and refine. It's not about replacing expertise, it's about giving your experts a head start so they can focus on what matters most. Here's another practical example: document summarization. Think about those lengthy submissions you get for public consultations, or those detailed call documents that need Q&A sections. AI could quickly pull out the key points, creating clear summaries that save everyone time, especially helpful for our colleagues working in their second language. Let's talk about meetings. No, we all spend a lot of time in them and even more time writing them up afterward. AI could take notes and create first drafts of minutes while you focus on the actual discussion. You'd still review everything, of course, but starting with a draft is much faster than starting with a blank page. But as impressive as all these tools and techniques are, I think that lost in the noise about AI, there's a much more fundamental breakthrough we need to talk about. What I want you to understand, consider, debate, and then hopefully leverage is that the true revolution that was unleashed on the world is not that these tools can generate, analyze, and summarize all sorts of information very quickly and easily, as useful as that is, but that they can do so based on a natural language interaction with human beings. For the first time in human history, we have managed to bridge one of humanity's oldest and most consequential technologies, language itself, with its newest technological advancements, artificial intelligence and neural networks. I was on an open-top bus tour in Thessaloniki, Greece last summer. I spent a good few minutes untangling a set of headphones, then plugging them into a little speaker system that had me select one of about 8 languages, at which point I was then joined by a faint, disembodied voice that was in the middle of a narration about a stop we were due to arrive at. So far, so fine, I suppose. While listening to the history of Thessaloniki, named after Alexander the Great's sister, I was fascinated yet felt unfulfilled. I realized I was in the birthplace of logic, reason, knowledge, and empiricism, but that I was a passive bystander, limited in my ability to interact with the wealth of knowledge encapsulated in the rich history of this place. I wanted a different relationship with that knowledge. I wanted to ask Thessaloniki a question, ask her about her half-brother Alexander and whether he was some genius or a madman. Ask her about some obscure but fascinating political intrigue in the 3rd century BC, or talk to Aristotle, the legendary Greek philosopher, and ask him about the nature of reality and if I really should have wine after ouzo. And it turns out I'm not alone in having this desire to communicate across space, substance, and time.
But I can't ask Aristotle a question. I mean, I can, but I won't get an answer. And so my hope is that in our lifetimes, we can make a tool of a new kind, of an interactive kind.
As we looked at earlier in my talk, humans have been striving for millennia to optimize our relationship with knowledge, to make it easier to store, understand, and ultimately leverage that knowledge. We invented all sorts of breakthrough solutions to achieve exactly that, all of which is eclipsed by what's happening right now. Now, for the first time ever, we can expect more than just being spoken to. We can have a two-way conversation. AI suddenly opens the thrilling possibility of not just having knowledge and information speak to us through books, papers, journals, and articles, but for us to be able to talk back. We're moving from passive to active engagement with the knowledge we capture and store.
And so my hope is someday, when the next Aristotle is alive, we can capture the underlying worldview of that Aristotle in a computer. And someday, some student will be able to not only read the words Aristotle wrote, but ask Aristotle a question and get an answer.
I believe conversational AI is the future of how we work and engage with the world around us, and that we are on the verge of a natural language revolution that will forever change the nature of our work and how we relate to knowledge and information. This realizes the decades-old vision of a more rewarding human-computer relationship. The breakthrough is not AI-generated content, but natural language as the interface. The language of information processing used to be code. Now it's English, or Italian, or Flemish, German, Chinese, or Arabic. For the first time, we can have true conversations with a new kind of intelligence, and through that, with the knowledge and information that surrounds us, and at a scale and speed that would have been inconceivable 5 years ago. Imagine being able to speak to the aggregate of all scientific knowledge on food safety and receive summaries, visualizations, recommendations, and insights previously hidden, all in real time. This is no longer science fiction. This is happening right now, and it's becoming increasingly accessible.